In this session, we'll be focusing on computing the expected values for different types of random variables. What do we really mean by expectation? How do we compute the expectations? What are the different headers that come under the computations of expectations? Because computing the means, computing the variances, all lot of things do come under the scope of expected values. So we will be looking at all these aspects, even moments of random variables. All those things are typically computed under this session of expectation itself. So as a quick agenda for this session, we are looking at computing expected value of a random variable to start with. Once we are comfortable with calculating the expected value, we are moving towards the moments of a distribution of a random variable. Then we will look at a Chebyshev's theorem, which has more to do with the relationship between mean and standard deviations and the proportion or percentage of data that is lying between the mean and the standard deviations. So a Chebyshev's theorem, an interesting theorem to be looked at. Then we will also spend some time in terms of understanding the moment generating functions of the random variables, using these moment generating functions to compute the various moments. So when I say first order moment, second order moment, what do I really mean by them? How do I really compute them? All that is what we are looking at. Then we are also bringing in a few product moments wherein I am looking at two variables together. So if I have to look at the moments associated with the product of two variables, then what is that and how is that I can look at? Then the next part we are looking at is the moments of a linear combinations of the random variables, right? If I'm talking of x is a random variable, then what about ax plus b? So some such kind of things we are going to look at here, and we would be ending this session with a discussion on conditional expectations. So overall this session is about computations of different types of expectations. Alright, so just getting started. First we will go with the discrete case. When we are using the word expected value of a random variable, in case of discrete, right now if I am simply saying x is a random variable which is about the number that comes up on the dice. So x can be 1, 2, 3, 4, 5, 6, any one of them. And the probabilities that are associated with x is 1 by 6 across. This is very simple example to look at. Now what we say is the expected value for this particular random variable is, this is a discrete random variable. So what we say is it's a sum of the products obtained by multiplying each value, these are the values of the random variable, by the corresponding probability. So it is as good as saying 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6. So this is what we are calling as the expected value of the random variable, which will be 21 by 6, which would work out to 3.5. Right? So sum of the products obtained by multiplying each value of the random variable. So what are the possible values the random variable can take? Multiply each value of that random variable by the corresponding probability. So expected value of x is nothing but x times f of x. F of x is associated with the probability. We have already seen f of x is the probability distribution function associated with the discrete random variable. You are multiplying it with x, which is the value that the random variable is taking, and you are summing it over all the values of x. And in case of continuous, the same example takes the same explanation. We will be doing x times f of x, but instead of summation, we would be integrating it over minus infinity to plus infinity. So let's look at this example to start with. The first one being a discrete case. A lot of 12 television sets includes two with white cots. Okay, so there are 12 television sets, out of which two of them have white cot. If three of the sets are chosen at random for shipment to a hotel, how many sets with white cots can the shipper expect to send to the hotel? So I'm talking about overall we are sending three of them, right? So f of x here, for whatever it is, I'm sending three sets. So it could be whatever is the x, 2cx, and based on the remaining 10 which are don't have any kind of white cards, I am saying 2cx times 3 minus x. This is the number of ways in which x number of white card televisions can be sent. 2cx into 10c 3 minus x, because I'm sending x number of televisions with white cards. So there are only two of them. So I can send 2cx ways, and because I am sending or x only x of them, the remaining 3 minus x should be sent from the non-white card television set. So overall I am sending 3 of them, so it would be 12c3. So I know f of x is this much at least. So based on this I can find out what is my f of 0. 2c0 is 1. 10c3 divided by 12c3. So 10 into 9 into 8 divided by 12 into 11 into 10. So 3 threes, 3 fours, 4 ones, 4 twos, 6 by 11. So 6 by 11 is the probability that 0 white cards would be sent. If I'm going with 1, 2c1 is 2, 10c2 is 45 divided by 12c3, 12 into 11 into 10, right? 5 twos, 5 nines, 2 2, 3 threes, 3 fours, 3 by 44. Again I can have, okay, so f of 1, 2c1 into 10c2 divided by 12c3. So working out to, okay, 90 divided by 12 into 11 into 10, right? 12c3, 12 factorial, and I need to have by 6 as well. So this is 2. This is 9. So it becomes 9 by 22. Sorry. So 9 by 22 for f of 1, and f of 2, 2c2 is 1, 10c1, 10c1 is 10 divided by again 12c3. So this becomes 1 by 22. So it is like 6 by 11 for f of 0. So up to here we know f of 0 is 6 by 11, f of 1 is 9 by 22, and f of 2 is 1 by 22. Now, if Okay, so if 3 sets are chosen at random for shipment to a hotel, how many sets with the white cards can the shipper expect to send? So 0 white card sets can be sent with a probability of, so if I take the random variable x, it could be either 0, 1 or 2. The probability of that x is 6 by 11, 9 by 22, 1 by 22. Now if I add these, it is 1, right? 6 by 11 is nothing but 12 by 22, 12 plus 9, 21 plus 1, 22 by 22. So it's a probability distribution function. Now the expected values is 0 multiplied by 6 by 11 is 0. 9 by 22 into 1 is 9 by 22 plus 1 by 22 into 2 is 2 by 22. So making it 11 by 22, which is nothing but zero point 0.5. So on an average, I can expect zero point 0.5 televisions to be shipped. 0.5 televisions with white cards is what I can expect to be shipped. Right? So though it is, so here the expected value is not used in a colloquial sense. I will not send zero point 0.5 television altogether, right? It's kind of an interpreted as an average. If I am repeating the same experiment so many times, on an average, the number of white televisions that are getting sent would be around 0.5. So that's the way you can work this out. Now the same way we will try it for the continuous case, where we are seeing the second example. We can see this example. Certain coded measurements of the pitch, diameter of threads of fitting have the probability density. So this is the probability density value, f of x equal to 4 by pi into 1 plus x squared, where x is lying between 0 and 1 and it is 0 elsewhere. I want to find the expected value of this random variable. So we said 0 into elsewhere, so I don't need to bother. I have to just take this area 0 to 1, x is x times f of x. F of x is 4 by pi into 1 plus x squared dx. Right? So I could very well say x squared equal to t, by which it becomes 2x dx equal to dt. So because x squared equal to t, and this is the range of the 0 to 1 is the range for x, now I have to convert it into t. So which would also be 0 to 1 only, because 0 square is 0, 1 squared is 1. So 4, so I'll write it as 2 into 2x dx, I take it as dt by pi, and this 1 plus x squared, I could have taken 1 plus x squared as t, right? That would have been much better. Or I can very well take it as 1 plus t, or let me do the other way. Let me take 1 plus x squared as t. So it becomes 2x dx. This is equal to dt. Right? Now I am talking about integrating between 0 and 1, x times 4 by pi into 1 plus x squared dx. So because I have taken 1 plus x squared equal to t, so this would be 1 plus 0 squared. So this is 1, right? T is 1, and 1 plus 1 squared, 1 plus 1, 2. So this is becoming 2. And because 2x dx is dt, I'll write it as 2 times 2x dx, I'll write it as dt by pi. 1 plus x squared is t. So this is what is happening. So 2 by pi, I'll take it out as a constant. Integral between 1 to 2, 1 by t is nothing but log t. right? 1 by t, the integral is log t, which I would be integrating between 2 and 1. So it works out as 2 by pi times log 2 minus log 1. Log 1 is 0. So it becomes 2 by pi times log 2 or log 4 divided by pi. So this is the typical expected value for this particular random variable. So you are doing a simple integrations wherever possible, finding out the expected value of the random variable by multiplying it by multiplying each probability density function with its corresponding value in case of continuous, and integrating it across and summing it across in case of discrete. Then the next important point that we are discussing here, if x is a discrete random variable, right, f of x is the probability distribution. So the expected value of g of x, something else, right, it's a function of x. See, here you are saying x is a discrete random variable. F of x is the probability distribution at x. So we are looking at the expected value of some other function g of x. So expected value of g of x is nothing but g of x times f of x, and you are summing it across. The same logic goes in case of continuous also. X is a continuous random variable. F of x is the value of its probability density at x. The expected value of g of x is coming out as g of x times f of x dx, which is integrated between minus infinity to plus infinity. So just for example, let's look at these two examples in case of continuous as well as in case of discrete. X is the number of points rolled with a balanced die. Find the expected value of g of x, 2x squared plus 1. So the expected value of g of x comes out as, across all the cases, I'm having g of x 2x squared plus 1 times f of x. F of x, we have seen that it is 1 by 6 direct. For each of the values it is 1 by x. So this you are doing a summation over 1 to 6 for x. So which is coming out as 1 by x 1 by 6 times 2x squared plus 1. If x is 1, 2 plus 1 is 3. If x is 2, 2 squared, 4 2's 8 plus 1, 9. 3 squared, 9 into 2, 18 plus 1, 19. 4 squared, 16 into 2, 32 plus 1, 33. 5 squared, 25 2's 50 plus 1, 51. And 6 squared, 36 2's 72 plus 1, 73. So the overall expected value is going to be 1 by 6 times 9 plus 3, 12, plus 19, 31, plus 33, 64, plus 51, 115, plus 73, 188. So working it out to 31. 616, 38. So 31, or probably will simplify it, 31 point something, or it could simply be written as 94 by 3. So this is the expected value, 2 into x squared, 2x squared plus 1 times f of x. If I am doing, finally it is working out to 94 by 3 for this particular numerical. Now let's look at in case of continuous. If x has a probability density of f of x equal to e power x for x greater than 0 and 0 otherwise, find the expected value of g of x equal to e power 3x by 4. So I know that probability density for f of x is e to the power of x, right? F of x is e to the power of x. So I could very well find out for x greater than 0, 0 to infinity. Let me just check if this is actually a probability density function or not. 0 to infinity e power x dx, which works out to e power x infinity to 0. E power infinity is infinity. So this can't be the case. So let's make it e power minus x, so that it becomes minus e power minus x minus 0 minus of minus 1, 1. Yeah. So make it e power minus x rather than e power x. Right? So in this case, I can very well find out the expected value of g of x for me is nothing but I am integrating it between 0 to infinity g of x, which is e power 3x by 4, multiplied by f of x e to the power of minus x dx. So working it out, 0 to infinity e to the power of minus x by 4 dx, which is nothing but e to the power of minus x by 4 by minus 1 by 4, which is becoming minus 4 times e to the power of minus x by 4, integrating it between infinity and 0. Minus 4 into minus 1 becoming 4. So the expected value of e power 3x plus 4, 3x by 4 is going to be 4 here. So that's one more way, especially if I want to find out the expected value of some other. So once I know the expected value of a random variable, once I know that some x is a random variable and I have the probability distribution function of x, then I can find the expected value of some other function of x, both in the continuous case as well as in the discrete case. A few important points for us in this context: whenever I want to find out expected value of ax plus b, I can very well do it as a into expected value of x plus b, because the same logic, if I put minus infinity to infinity, expected value of ax plus b is nothing but ax plus b times f of x dx. So I can very well write it as minus infinity to infinity a times or ax times f of x dx plus again minus infinity to infinity b times f of x dx. Now here we know this part, a, if I take out minus infinity to infinity x times f of x dx is nothing but the expected value of x, plus b times minus infinity to infinity f of x dx is nothing but 1. Right? Sum of all the probabilities should be equal to 1. So it is coming out as a into expected value of x plus b. Now if a is constant, right, a is constant, then expected value of ax is nothing but a into expected value of x. If b is constant, expected value of b equal to b. Then if I'm talking about C1, C2, C3 are constants, I'm talking about expected value of Ci times Gi of x is nothing but Ci times expected values of Gi of x altogether. So each individual expected value multiplied by its corresponding Ci. Look at this example. If the probability density, right, if the probability density of x is given by f of x equal to 2 into 1 by 1 minus x, where x is lying between 0 and 1 and it is 0 elsewhere. I want to find out the expected value of x power r, and after that I want to use it to find out expected value of 2x plus 1 whole square. So let me try this from the screen, from creating it as a white screen. So I want expected value of, let me go step by step, x power r. So I am integrating between 0 to 1 because f of x is lying only between 0 to 1. X power r, right, because that's a function of x power r, f of x 2 into 1 minus x dx. So this is going to come out as 2 when I take it out, integral of 0 to 1 x power r minus x power r plus 1 dx. So up to here it's fine. So here I am taking it as 2 into x power r plus 1 by r plus 1 minus x power r plus 2 by r plus 2. This is integrated between 1 and 0. So which is becoming 2 into 1 by r plus 1 minus 1 by r plus 2, which becomes 1 by 2 into 1 by r plus 1 into r plus 2, right? So this is what is becoming expected value of x power r. 2 into 1 by r plus 1 and multiplied by 1, 2 divided by r plus 1 into r plus 2. So now I want to find out expected value of 2x plus 1 whole square. So I could very well break it out, right? I'll take it as expected value of 4x squared plus 4x plus 1, right? So x power r, this is expected value of x power r. R is, so here I can take it as 4 into expected value of x squared, r is 2. So when r is 2, 2 divided by 2 plus 1 is 3, 2 plus 2 is 4. 2 divided by 12, which is 1 by 6, plus 4 into expected value of r is 1. 2 divided by 1 plus 1, 1 plus 1 is 2, 2 into 2 is 2 into 2 plus no, 1 plus 2 is 3, so 2 divided by 6 plus 1. So it is 4 by 6 or 2 by 3 plus 4 by 3 plus 1, which is what is working out to an overall number of 3. So this is how we can simplify the numerical in this particular example, right? Now I can also look at a couple of other examples as well, right? I have one good example. Let's say otherwise we'll take this up. So we are extending the same situation, right? If I'm talking about expected value of a random variable, we can extend this situation to more than one variable also. If I'm talking about x and y, discrete random variables, f of x comma y is the value of their joint probability distribution at x comma y, then expected value of g of xy is nothing but, again, each particular value of g of xy multiplied by its corresponding probability, and you are adding it up. In case of discrete, you are g of xy and f of xy are getting multiplied, and it is integrated between the ranges of x and y. So if you say, we can take up a couple of the numericals again, right? So if I want to find out expected value of g of xy, here f of xy is coming out to 2 by 7, right? F of xy So let's take this example itself. F of xy is 2 by 7 into x plus 2y, where x is between 0 and 1 and y is between 1 and 2 and 0 elsewhere. I want to find out the expected value of x by y cube, right? Not y3, it is y cube. So let's try this out. So I require expected value of g of x, which is x by y cube. I'll take it as integration between x, for x I am integrating between 0 to 1, y I am integrating between 0 to 2, g of x is x by y cube times f of xy, 2 by 7 times x plus 2y, I am having it as dx dy. So let's simplify this. There's nothing much to simplify. So I'll be taking it as, so let me take it on a fresh sheet, that would be better. So I have to take it as x is between 0 to 1, y is between 1 to 2, right? X by y cube, 2 I'll take it outside, x plus 2y, dx dy. So I'll write it as 2 times 0 to 1, 1 to 2, right? X squared by y cube plus 2x by y squared dx dy. So let me first integrate it with respect to x. So y I'll retain it 1 to 2. So x I am taking, so that's where it becomes 1 by y cube times x squared is x cube by 3. So x cube by 3 integrated between 0 and 1, it is 1 by 3 plus right, so I'll take 1 by y squared or 2 by y squared, I'll take it as constant. X is becoming x squared by 2. X squared by 2 is integrated between 1 and 0, which is 1 by 2. So this will be dy. So it becomes 2 into 1 by 3y cube. So I'll take it as 1 by 3 times y to the power of minus 3 plus y to the power of minus 2 dy. And this is integrated between 1 and 2. So 2 multiplied by 1 by 3. Now let's do the integration. Y to the power of minus 3 becomes y to the power of minus 2 by minus 2. Right, this has to be integrated between 2 and 1. And similarly, this has to be 2 into y to the power of minus 1 by minus 1. This is also integrated between 2 and 1. So the summation comes 2 into 1 by 3 times y to the power of minus 2. 2 to the power of minus 2 is 1 by 2 squared, which is 4. Right, so I'll take this 2 out also, which will make it minus 1 by 6. Right, so this becomes 2 to the power of minus 2 minus 1 to the power of minus 2 is 1. So this is the first part. 2 by minus 1 will become minus 2 times 2 to the power of minus 1 is 1 by 2 minus 1 to the power of minus 1 is 1. So this is becoming 2 into minus 1 by 6 into 1 by 4 minus 1 is minus 3 by 4. So it is becoming minus 3 by 4 into minus 1 by 6. So 3 by 24 or 1 by 8 is this part. And this is becoming minus 2 into 1 by 2 minus 1 is minus 1 by 2. So this becomes 1 by 4 plus 1, which is working out to 5 by 4. right? So you can very well plan out all this integration. I did not take 7 somewhere. I missed out 2 by 7. So let's do this again. Let me do this numerical again. So we have taken f of x comma y is 2 by 7 into x plus 2y, right? And I am looking at g of x comma y as x by y cube. So based on that, I am trying to find out expected value of x by y cube. Integrating x is 0 to 1, y is 1 to 2, g of xy is x by y cube, f of xy is 2 by 7 times x plus 2y. This whole thing dx dy. So I am trying to put it as 2 by 7 if I take out, right? Integration 0 to 1, 1 to 2. I take out 2 by 7 altogether outside, I'll handle it later. X squared by y cube plus 2xy, okay, it is 2xy by y cube. Some calculation issues came up, dx dy. So which is nothing but 2x by y squared, right? Now, if I'm simplifying it, let me take 2 by 7 out forever, we'll take it later. Now I'll integrate with respect to x first. So y I am taking it as constant, 1 by y cube, 1 by y cube, x squared I am taking it, so the 2 by 7 and this y integration is still there. X integration is x squared, which is x cubed by 3, integrated between 1 and 0, so it is 1 by 3, plus 2 by y squared. I am integrating x, so x squared by 2, integrated between 1 and 0, which becomes 1 by 2. So this whole thing is dy, right? So this is becoming 2 by 7 times integration of 1 to 2, 1 by 3 y cube plus 1 by y squared dy. So again, 2 by 7 is taken out. Now let's simplify this. 1 by 3 integration of 1 by y cube, which is y to the power of minus 3. So it becomes y to the power of minus 2 by minus 2. So minus 1 by 2y squared plus 1 by y squared will become y to the power of minus 2 plus 1, y to the power of minus 1 by minus 1. So minus 1 by y is becoming this one. And this is integrated again between 2 and 1. So it becomes 2 by 7 times minus 1 by 6, 1 by y squared, 1 by 4 minus 1, minus 3 by 4, minus 1 by y is becoming 1 by 2 minus 1, which is minus 1 by 2. So this is working out to 2 by 7 times 1 by, so this is 1 by minus 1 by 6 into minus 3 by 4, becoming 3 by 8, and this is plus 1 by 2. So this is becoming 3 by 8 plus 1 by 2, which is 7 by 8. and 7 by 8 is working out to, if I'm taking internally, it is working out to 1 by 4. So this is how we are simplifying this whole expression, right? Finally working out the values for this integral. So if there are some calculation mistakes, you can very well work them out. So that's how the whole thing is getting simplified too. All right. So that's the simplification that is going in here. Alright, so that's how we are computing the expected values of the random variables both in the continuous, discrete, univariate and multivariate cases. Alright. Now that we are clear about finding out expected value of a random variable, we will be moving now to finding out the moments of the distribution of a random variable. We'll talk about different kinds of moments, right? So we will talk about the moments about the origin, one set, and we will also talk about the moments about the mean. There are two major types of moments that we are talking of: moments about the origin, moments about the mean. So if you look at the first one, the rth moment about the origin of a random variable x is the expected value of x to the power of r. That is what we are calling as the rth moment about the origin. So which is denoted as mu r dash, right? Mu r dash is the rth moment about the origin. So which is nothing but, in case of discrete, x to the power of r times f of x and then summation over all the values of x. And in case of continuous, it is x to the power of r times f of x dx integrated over minus infinity to infinity. So r equal to 0, right, which is nothing but expected value of x to the power of 0, which is expected value of 1. So when r equal to 0, the 0th moment about the origin is always equal to 1. And when r equal to 1, it is nothing but expected value of x, which is nothing but the mean. So mean is the first moment about the origin. So moments, typically we use them to understand the shape of the distribution, right? We will be seeing when we are drawing the shape of the graph of the probability distribution in case of discrete, or the density function in case of continuous. The primary intention of understanding the moments is to get a good hold regarding the shape of the distribution. So that is one set of moments generally we compute, which are called moments about the origin, which is nothing but expected value of x to the power of r. Whereas on the other side, we also have the moments about the mean. So the rth moment about a mean for any random variable x is nothing but, it's the expected value of, see, if I say expected value of x to the power of r, it's the rth moment about the origin. But if I take expected value of x minus mu to the power r, then we are calling as the rth moment about the mean. So when I'm setting mu r, it is expected value of x minus mu to the power r, which is nothing but x minus mu to the power r multiplied by f of x and summed over all the values of x in case of discrete. And similarly in case of continuous, x minus mu to the power r multiplied by f of x dx, which is integrated between minus infinity to infinity in case of continuous. Now here a few important central moments, if you see, few important moments about the mean. If you set r equal to 2, which is nothing but expected value of x minus mu whole square. This is what we typically call as variance. Expected value of x minus mu whole squared is what we are calling as variance. And even this is indication of the spread or the dispersion of the distribution of a random variable. So we are calling it as variance, and the positive square root of this variance is what we are calling as standard deviation. So one important inference that we can draw: larger the variance, the greater the probability of getting a value that is not close to the mean. So if the variance is very large, I'll get very dispersed values very much away from the mean. So the chances that I'll get any value very close to the mean is very lesser. But on the other side, if the variance is much smaller, it means that majority of the values are more or less concentrated around the mean itself. So the chance that my observations will be very close to the mean would be much higher if the standard deviation or the variance is lesser. And as the variance keeps increasing, the dispersion of the data from the mean also increases. So that is one of the reasons for a large number of data variables, we would be computing the mean as well as the variance also. Then, and similarly, I can have skewness. Skewness is nothing but it's the third moment about the mean, which is expected value of x minus mu whole cube. This talks about whether my data is very much close to symmetric or there is a lot of asymmetry in the data, which is causing the data to be more and more positively skewed or negatively skewed. So that's how we can compute different kinds of moments associated with the distribution of a random variable. So we can very well take up with respect to, let's say, the computation of the variance, right? We said sigma squared. Let me try solving this. We have said variance is nothing but expected value of x minus mu whole squared, which is otherwise expected value of x squared minus 2 mu x plus mu squared, which works out as, if I expand it separately, expected value of x squared minus 2 mu times expected value of x plus mu squared. Mu squared is again, okay, I'll take it like this, which is otherwise expected value of x squared minus 2 mu into expected value of x is nothing but mu. So it becomes minus 2 mu squared plus mu squared. So which is becoming expected value of x squared minus mu squared, which is nothing but expected value of x whole square. Right? So this is how you are able to derive the variance of the distribution. Same way you can plan out with your skewness as well. So when I am looking at skewness, it is expected value of x minus mu whole cube, which becomes expected value of x cubed minus 3 mu x squared plus 3 mu squared x minus mu cube. So it becomes expected value of x cubed minus 3 mu times expected value of x squared plus 3 mu squared times expected value of x is again mu plus minus mu cube. So overall it becomes expected value of x cubed minus 3 mu expected value of x squared plus this is 3 mu cube minus mu cube, which is plus 2 mu cube. 2 into expected value of x whole cube. So this is what is the formula for skewness. So either of the ways, so I am able to convert the central moment into the moments about the origin. So when I know the moments about the origins, I can very well compute their central moments as well. So this is how I can look at this specific numerical. Now going back to a couple of examples out here, calculate the variance of x representing the number of points rolled with a balanced die. So I already know the expected value of x, because the random variable x can take 1, 2, 3, 4, 5, 6 with probabilities of 1 by 6 each, right? Across the probabilities are 1 by 6. So based on this, I'll get expected value of x is nothing but multiplying and adding it. I will get it as 3.5 or 7 by 2. Now, if you are talking about finding out the variance, it is expected value of x minus mu whole squared, or I can do it as expected value of x squared minus expected value of x whole squared. So if I want expected value of x squared, I square these things and multiply by 1 by 6, right? So the squares are 1, 4, 9, 16, 25, 36. 61, 77, 86, 90, 91. 91 by 6 is what is expected value of x squared. So based on this, I can find out my variance as expected value of x squared minus expected value of x whole squared, 49 by 4. So which works out to, this is 182 minus 147, giving me 35 by 12. 35 by 12 will give me the variance associated with this particular set of values. Alright. Okay. Now let me look at another example, the continuous case. Certain coded measurements, right? I'm looking at another example. Certain coded measurements of the pitch of the thread fitting having the probability density. So this is the probability density function. Corresponding to this, I want to find the standard deviation of the random variable, right? So let me try this. Again, we can use the same expected value of x squared minus expected value of x whole squared, right? So let me try 4 by pi, right? We are talking about what is the f of x? 4 by pi into x by 1 plus, no, 1 by 1 plus x squared, right? Let me just go back to the data. 4 by pi into 1 plus x squared. This is what is our f of x, where we are talking of x equal to, x is lying between 0 and 1. So we have already computed the expected value of x for this, where we have computed as log 4 divided by pi. In our earlier examples, we have found it out. Log 4 divided by pi is the expected value of x. So let's find out expected value of x squared for this. So I'll take it as 4 by pi times, I'll integrate it between 0 and 1, x squared multiplied by 1 by 1 plus x squared dx. So this I can very well write it as, right, if you remember the way you solve this kind of problem, I'll write, instead of x squared divided by 1 plus x squared, I will try to write it as 1 minus 1 by 1 plus x squared dx. And in this format, I'll try to make 1 plus x squared equal to t. And based on that, 1 plus x squared equal to t. So x squared will be t minus 1 right? And 2x dx. No. How do you solve 1 by 1 plus x squared? So here I can very well take otherwise x equal to tan theta. If I take x is tan theta, dx will become secant square theta, right? The dx will become secant square theta d theta, and we can transform 1 plus x squared is 1 plus tan square theta, which would be secant square theta again. And even this interval we can change, so we can make it 4 by pi times. So I'll take the integral of this separately. For 1, the integration is x, which is integrated between 1 and 0, and for this part it is 4 by pi times 1 by 1 plus x squared, 1 plus tan squared theta becoming secant square theta, and dx is secant square theta d theta. And in this case, the integral is happening between, instead of 0 and 1, 0 equal to tan theta. So because 0 equal to tan theta, so theta will be 0. 1 equal to tan theta, so theta will be pi by 4. So this one will be 4 by pi minus 4 by pi into, if you look at this values, so this is coming out to be 1, right? Secant square theta is typically coming out. So which is coming out as pi by 4. So overall it is working out to 4 by pi minus 1. Right? So it is coming out as 4 by pi minus 1. So this is the value that is associated with expected value of x squared. So now I can very well find out variance, which is expected value of x squared minus expected value of x whole square. So whatever I simplify, whatever I get, that should be the variance associated with this data. Taking the positive square root of it will give me the standard deviation part. Correct? Alright. So let's move on to the next aspect. And a few important points in this context. If x is having a variance of sigma squared, then the variance of ax plus b will be a squared times the variance of x, and plus b does not have any kind of an impact, which means addition of a constant to the values of a random variable will shift all the values of x to the left or to the right by the extent of constant. So there is no impact on the spread of the data at all. So standard deviation or the variance do not get impacted because of addition of some specific value. But if they are multiplied by a constant, the variance is always multiplied by the square of the constant. So a couple of important points that you may have to remember in this particular context, which is very much important for us to understand, right? So these are some of the things which are more specific to the moments of the distribution of a random variable. Then we'll move on to the next important topic in the session, which is the Chebyshev's theorem, or sometimes people call it as Chebyshev's inequality. So this is one important theorem which clearly suggests that variance is a very important indicator of the dispersion in the data. Dispersion of the distribution in the random variable, if I really have to find out, it is where I am looking at the Chebyshev's theorem itself. What the theorem simply says is, you know that the mean is mu, sigma is the standard deviation of a random variable x. What it says is, for any positive constant k, the probability is at least 1 minus 1 by k squared that x will take on values within k standard deviations of the mean. So if this is the mean standard deviation, right, if this is a random variable, this is the mean, this is the standard deviation, what it says is, if at all I am talking of a value, let's say between mu plus 2 standard deviation and mu minus 2 standard deviations, what it says is the probability is at least 1 minus 1 by k squared, 2 squared. If I say this is k standard deviation this side or k standard deviation this side, if my value has to be between minus k standard deviations to plus k standard deviations region of the mean, what it says is the probability is at least 1 minus 1 by k square. So if I have to say I am randomly picking up some value, and if I have to say that that value will lie between mean minus 2 standard deviations to mean plus 2 standard deviation, the probability will be at least 1 minus 1 by 2 squared, which is 0.75. So there is a minimum of 0.75 chance that a value will lie between plus or minus 2 standard deviations of the mean. Only 0.25 chance or 25% chance that the values will be either below the 2 standard deviations level or much above the 2 standard deviations level of the mean. So that is minimum. So it could be only greater than that, that the probability will lie between those plus or minus k standard deviations of the mean. Very, very rare chances that it will go much beyond that particular number. That is what is being suggested by Chebyshev's inequality. Whatever is the kind of the data we are talking of, the moment you compute the mean of it, the moment you compute the variance and standard deviation of it, we can very well say what proportion of the values of the data lie within the plus or minus k standard deviations of the mean. A minimum of 1 minus of 1 by k squared percentage of the values lie plus or minus k standard deviations from the mean. Or even if I am converting the same into the probability concept, there is at least 1 minus 1 by k squared probability that a value will lie between plus or minus k standard deviations from the mean. So the probability of modulus x minus mu less than k sigma is always greater than 1 minus of 1 by k square. So this is what is the example even I demonstrated now. The probability is at least 0.75 that a random variable x will be within the plus or minus 2 standard deviations of the mean. So based on that, I can very well conclude that sigma is the one that is controlling the spread or distribution or dispersion of the distribution of a random variable. But one point we really need to be understanding here is the Chebyshev's theorem only assures that the probability cannot be less than 1 minus 1 by k squared. It does not give what should be the probability. It only gives me the lower interval that the probability cannot fall below this. That's the only thing that is being suggested by the Chebyshev's inequality. So just look at one numerical in this context. If I talk about the probability density function of x, 630 x to the power of 4, 1 minus x to the power of 4, where x is between 0 and 1 and 0 elsewhere. Find the probability that it will take on a value within 2 standard deviations of the mean, and compare this probability with the lower bound that is provided by the Chebyshev's theorem. So I want to see whether for this it is lying between plus or minus 2 standard deviations of the mean. I want to find out what is the probability that it will lie within plus or minus 2 standard deviations of the mean. So let's try finding out first of all the mean and the standard deviation for this. So f of x is 630 x to the power of 4, 1 minus x to the power of 4. So if I look at this, this is nothing but 630 x to the power of 4 into, if I expand this, this is nothing but 1 minus 4x plus 6x squared plus minus 4x cube, a binomial distribution, right? A binomial expansion, plus x to the power of 4. So that way it becomes 630 times x to the power of 4 minus 4x to the power of 5 plus 6x to the power of 6 minus 4x to the power of 7 plus x to the power of 8. Okay, now let me find out the mean of it, right? Expected value of x. So I will be trying to find out all these numbers. 630 times, I have to take the integrals of all of them integrated between 0 and 1, right? So x to the power of 4, it is x to the power of 5 by 5, which is 1 by 5, minus 4 into x to the power of 5, x to the power of 6 by 6, 1 by 6, plus 6 into x to the power of 7 by 7, it is 1 by 7, and sorry, I have to, now if I am talking about expected value, I have to multiply it with x and then take the expected value, right? So 630 times x into this, x to the power of 5. So it becomes x to the power of 6 by 6 minus 4 into, this is x to the power of 6. So x to the power of 6 will become x to the power of 7 by 7, which is 1 by 7, plus 6 into, this becomes x to the power of 7, so x to the power of 8 by 8 is 1 by 8, minus 4 into x to the power of 8, 7 will become into x means x to the power of 8, x to the power of 9 by 9, which is 1 by 9, and this will become x to the power of 9, so which will be x to the power of 10 by 10, which is 1 by 10. So the mean of this will become 630 into 630 into 1 by 6 minus 4 by 7 plus 3 by 4 minus 4 by 9 plus 1 by 10. Right, if I am looking at the LCM of these things, if I say it is 630, it is 105 minus 360 plus, oh, here it is not getting divisible, so 630 does not come in out here, so it should be 1260 then, right? It has to be 1260. So going with this, it is 210 minus 720 plus So here it is 315 times 3, 435 minus 140 times 4, which is 560 plus 126. So this is coming out to 210. Oh, negative, it is working out to be negative. So somewhere things might have gone wrong. So if you look at this, I think here there is a mistake. 315 into 3, 315 into 3 is 945. So this is becoming 210 plus 945, which is 1155 plus 126, which is 1281 approximately, minus 1280, which is coming out as 1 by 1260, multiplied with 630. So which is coming out to 1 by 2. So here the mean is coming out to 1 by 2. Now I can very well look at the expected value of x squared as well. So I will multiply this with x squared, and after that I'll take the integral, right? So if I multiply it with x squared and then take the integral, which is nothing but x power 6 is x power 7 by 7, 1 by 7 minus 4 by 8, right, plus 6 by 9 minus 4 by 10 plus 1 by 11. This is the expected value of x squared. So which I could very well simplify it. So this I can call it as 1 by 2. This I can call it as 2 by 3 to be on the simpler terms. And this I can call it as 2 by 5. So it can work out to me as 5 into 2, 10. 10 into 21 is 210. 210 into 11. This is what I can take as the LCM. So 7 into 30. 30 into 11. 330 minus this 2 becomes 105 into 11. 1050 and another 105. It is 1155. This becomes 3 means 70 into 11, 770. 770 into 2, which becomes 1540, right? And this is minus 2 by 5. So 42 into 11, 462 into 2, 924 plus 210. So I can look at this 330 plus 210, 540. 540 plus 1540 becoming 2080 minus 1155 and 924 becoming 2079. So even this is equal to 1. So it is also becoming 630 into 1 by 210 into 11, which is becoming 3 by 11. Sigma squared, expected value of x squared. So this is expected value of x squared, which is becoming 3 by 11. So variance for us is nothing but expected value of x squared minus expected value of x whole squared. Expected value of x squared minus expected value of x is 1 by 2 whole squared. So this will become 1 by 44. So here till now I have got the mean is, till now I have got mean is 1 by 2, expected value of x, which is the mean, I've got as 1 by 2. The variance of x, which is expected value of x squared minus expected value of x whole squared, is coming out to 1 by 44. So based on that, the standard deviation is square root of 1 by 44. Right, and if I am looking at 1 by 44, probably around 1 by 44, the square root of 44, if I am looking at 7.5 or something, so this entire thing is around 15%. So I can take it rounded off to 0.15 being the standard deviation. So mean is around 0.5, standard deviation is around 0.15, so plus or minus 2 standard deviations is between 0.2 to 0.8. So I'll try to find out the probability that it will lie between 0.2 to 0.8. So 630 into x to the power of 5 minus 4x to the power of 6 plus x to the power of 4 minus 4x to the power of 5 plus 6x to the power of 6 minus 4x to the power of 7 plus x to the power of 8. The probability that this is lying within this range. So you could simplify this saying 630 into x to the power of 5 by 5, right? So zero point 0.8 to the power of 5 minus 0.2 to the power of 5 divided by 5. So this way you can very well simplify, and this number should be very much greater than this number if we can simplify it, right? X to the power of 5 by 5, 0.8 to the power of 5 minus 0.2 to the power of 5. So let me try putting it into the spreadsheet. Right, I can put it in a spreadsheet and I can look at it. Or you can use a calculator to solve it, whatever it is. So if you see the first term, it has to be 1 by 5. So 1 by 5 into 0.8 to the power 5 minus 0.2 to the power 5. So this is the first part, right? Then it is 4 by 6 into 0.8 to the power 6 minus 0.2 to the power 6. So this is the second term. The third one is, this is 4 by 6, so this is 6 by 7 into 0.8 to the power 7 minus 0.2 to the power 7. So this is giving me the third term. The fourth term is working out to 4 by 8, which is 0.5 times 0.8 to the power 8 minus 0.2 to the power 8, which is this much. And the fifth term is coming out to 1 by 9 times 0.8 to the power 9 minus 0.2 to the power 9. So these are the various things that are working out, right? All these numbers, and you are multiplying the same 4 by 5 into this. The overall is coming out to 0.59, right? If you look at 0.2 to 0.8, right? It is working out to integration between zero point 0.2 to zero point 0.8. I'm taking 630 into x to the power of 4 minus, right, x to the power of 4 minus 4x to the power of 5 plus 6x to the power of 6 minus 4x to the power of 7 plus x to the power of 8. So it is 1 by 5 into zero point 0.8 to the power of 5 minus 0.2 to the power of 5. So 1 by 5 into zero point 0.8 to the power of 5. Similarly, 4 by 6 into zero point 0.8 to the power of 6 minus 0.2 to the power of 6. You are trying to simplify this. This is working out to be this much. Okay. So there are some positives and negatives. So this is this plus this plus this minus this minus this. So it is 0.001, and this number you multiply it with 630, which is giving you 0.96, almost 96% probability. But as per the Chebyshev's inequality, it should be only 75%. So in this case, you are seeing that at least 96% of the observation, there is a 96% chance that the value would lie between plus or minus 2 standard deviations of the mean itself. But as per the Chebyshev's inequality, only 75% of the values should lie within plus or minus 2 standard deviations of the mean. So that way I have very much I have taken care of the Chebyshev's theorem, and my data is very much meeting the Chebyshev's inequality overall, right? Now, moving on to the next topic, wherein I am looking at moment generating function. So we have already computed the moments using the expected value of x to the power of r. If we wanted moments about the origin, r we have taken it as expected value of x minus mu to the power r when we wanted to compute the moments about the mean. But when we use this moment generating function, it's an alternative method to find the moments of the distribution. So we really don't need to do that summations wherein x power r multiplied by f of x, summing it over all the x, or x power r multiplied by f of x, integrating it over all the values of x from minus infinity to infinity. So that's a regular procedure. Whereas when we are talking about moment generating functions, we really don't need to do that activity, because as a part of this moment generating function for this random variable, if at all it exists, is generally given by expected value of e to the power of tx. So which means you just multiply e to the power of tx by f of x over all the values of x, or in case of continuous case, you do a e to the power of tx multiplied by f of x, integrate it with respect to x from minus infinity to infinity, and the independent variable in this case will be the t. And the reason why this came up, we know that e power tx is nothing but, if I expand it, 1 plus tx plus t squared x squared by 2 factorial plus t cube x cube by 3 factorial plus so on. This is an infinite series, right? So if you are trying to multiply this with f of x, so this whole thing, so when you are saying e power tx into f of x, this whole thing is getting multiplied with f of x, right? This whole thing is getting multiplied with f of x and then added. So individually now if you take t out, so if you are primarily looking from this corner itself, 1 into f of x, which is f of x plus t times x into f of x, right, when you are doing a summation. So individual summations again. Similarly, you have t squared by 2 factorial times x squared into f of x. So now you could see this is nothing but expected value of x. This is nothing but expected value of x squared. So you are getting the moments by substituting the values of t, right? So this is the reason we are getting this as a moment generating function altogether. This is what is called as a moment generating function, because all the moments can clearly be generated by looking at by creating one such kind of an expression associated with expected value of e power tx. Now we can just see a couple of examples. Find the moment generating function of the random variable whose probability density is given by e to the power of minus x and use it to find the rth moment. Let's see. So f of x I have got as e to the power of minus x. So I have to find out the moment generating function of x, right? Moment generating function is nothing but expected value of e to the power of tx, which means I am doing an integration because this is only x greater than 0. Instead of doing it from minus infinity to infinity, I am doing it only with respect to, right? So it is e to the power of tx, which is g of x multiplied by f of x, which is e to the power of minus x dx, which will very well work out to 0 to infinite e to the power of t minus 1 into x, or e to the power of minus x into 1 minus t dx. So this is nothing but, if you look at it, so this is e to the power of, if you are doing an integral, e to the power of minus x into 1 minus t, or e to the power of 1 minus t into x divided by 1 minus t, and this you integrate it over infinity to 0, right? E to the power of 1 minus t into infinite. So which is working out to, so when you are talking about infinite and otherwise minus x, so minus infinite into t, so which is becoming 0, and this is becoming 1. So overall this is becoming 1 by 1 minus t, where t is less than 1. If t is less than 1, so 1 minus t times x is becoming, this part is e to the power of minus infinity, which is becoming 0, divided by 1 minus t. So this is what is becoming the moment generating function, right? If you simply see this, this is nothing but 1 minus t to the power of minus 1. I can very well write this 1 minus t to the power minus 1, which is nothing but 1 plus t squared plus t cube plus so on t to the power of r, right? So that is, so you are getting the entire moment generating function associated with each one of them. But if you really see, this is what we are getting. I have to take the coefficients associated, because we have to establish them as t squared by 2 factorial and so on. So 1 plus, what I'll do is 1 factorial times t by 1 factorial, 2 factorial times t squared by 2 factorial. If I multiply and divide 3 factorial times t cube by 3 factorial and so on, the coefficient of t by 1 factorial, which is 1 factorial, is the first moment. The second moment is 2 factorial. The third moment is 3 factorial, which means the rth moment here is nothing but r factorial. For this example, r factorial is ending up as the rth moment for this particular distribution, because we are able to establish 1 by 1 minus t in this form, and I know that if I have to establish mx of t, it has to be like 1 plus mean times t, 1 plus whatever is the expected value of x, right? We have seen earlier 1 plus expected value of x times t. Then you have the second moment, expected value of x squared times t squared by 2 factorial, expected value of x cube, which is the third moment, times t cube by 3 factorial. So this is the typical expansion of the moment generating function, and for this example it came out like this. So converting this into this kind of a format says that the rth moment is r factorial for this kind of a example. Alright. Now, the main difficulty in using this kind of expansion, if you see here 1 by 1 minus t, I have made it as 1 minus t to the power minus 1, and after that we have expanded it. So expanding into a Maclaurin series is the most difficult part when we are using this kind of moment generating function. Okay. And the other way, if I already have a moment generating function, right, I already have a moment generating function, then if I have to find the rth moment, you take the derivative of that moment generating function, right? If you already have the moment generating function, you take the derivative. Now I got 1 by 1 minus t as my moment generating function in the earlier example, right? So what I can very well do is, I can take the derivative of this. What is the derivative of 1 by 1 minus t? So I can take it as 1 minus t times the derivative of 1 is 0, minus 1 times the derivative of minus 1 times derivative of 1 minus t is minus 1, divided by 1 minus t whole square. So it is nothing but 1 by 1 minus t whole square. This is the derivative, and at t equal to 0, if I have taken the first derivative, I am putting t equal to 0, which means 1. So the when we are talking of rth derivative, I have taken the first derivative, right? So the first derivative is nothing but expected value of x, the first moment. So it's expected value of x, which is nothing but, when I'm setting t equal to 0, which is coming out to be 1, 1 is the first moment, which is expected value of x is 1 for this particular item. Now if I want to look at the second moment, expected value of x squared, take the second derivative of this, which is nothing but, so if you are taking 1 by 1 minus t whole squared, which is nothing but 1 minus t to the power minus 2, right? So the derivative of this becomes minus 2 into 1 minus t to the power minus 3 and minus 1. So this becomes 2 by 1 minus t whole cube. This is the second derivative. Substitute t equal to 0, which will become 2. 2 will be the second moment, which is expected value of x squared for this example will be 2. So this is one more way in terms of finding the moments from the moment generating function. You take a derivative of the moment generating function, right? If you already have the moment generating function, take the derivative of that. If you are taking the first derivative, you will get the first moment about the origin. If you take the second derivative, you will get the second moment about the origin. So if a function in an expanded as a power series, the coefficient of t power r by r factorial is the rth derivative. So either I take the rth derivative or I should be able to expand something into a Maclaurin series. So expressing it as an rth derivative looks much more simpler rather than expanding it into a Maclaurin series, right? So we can look at the example just for a quick understanding. Given that x has a probability distribution of this much, right? F of x is given like this. For x equal to 0, 1, 2, 3, find the moment generating function for this and then use it to determine the first two moments. So let me find out the moment generating function. So I was given f of x is 1 by 8 times 3cx. This is what is my f of x for x equal to 0, 1, 2, 3. So I know that the moment generating function mx is nothing but expected value of e to the power of tx. So which is also nothing but, if I am taking 1 by 8 out, right, it's a sigma summation from 0 to 3 e to the power of tx into 3cx. So the same thing works out if I am expanding it from 0 to 3. So I'll take 1 by 8 out, e to the power of tx, 3c0 is 1, right? When you are setting x equal to 0, when you are setting x equal to 0, e power 0 is 1. So this is whole thing will become 1. Then when your x is 1, e power t and 3c1. So this is 3e power t. Okay. Then your x is 2, e power 2t, 3e power 2t. And when your x is 3, e power 3t and 3c3 is 1. So this is what you are getting, 1 by 8 into 1 plus 3 e power t plus 3 e power 2t plus e power 3t. So it is nothing but 1 plus e power t whole cube, right? This is an expansion of 1 plus e power t whole cube. This is what is coming out as the moment generating function. Either I can leave it here or I can keep it here. So this is the moment generating function for me. Now I want to use it to find out the first moment. So which is expected value of x. So I take the derivative of this 1 by 8, 3 into 1 plus e power t, right? And the derivative of e power t is e power t. 3 into 1 plus e power t squared, and derivative of e power t is e power t. This is the first derivative. So in this first derivative, I will set t equal to 0. So it becomes 3 by 8 into e power 0 is 1. 1 plus 1, 2 squared, which is 4. E power 0 is again 1. So overall it is working out to 3 by 2. This is the first moment or the mean. Now if I look at the second moment, which is expected value of x squared, take the second derivative. Okay, 3 by 8, take it out. 1 plus e power t whole squared into e power t. So I'll use the multiplication formula. 1 plus e power t whole squared into e power t plus e power t into 2 into 1 plus e power t into e power t. So this is what is the derivative, the second derivative. Okay, now set t equal to 0. E power 0 is 1, 1 plus 1, 2, 2 squared is 4 into e power 0 is 1 plus e power t again, e power 0 is 1 into 2 into 1 plus 1. So this is also becoming another 4. So which is working out to 3 by 8 into 8, which is nothing but 3. The second moment is getting operated at 3. So we are able to generate a moment generating function, and based on that moment generating function I take the derivatives at t equal, I take the rth derivative and substitute t equal to 0 in it to arrive at the rth moment for a particular data, right? So that is what is this example. I hope it is clear. Then a few interesting points regarding the moment generating functions, right? We have talked about the moment generating function of x, but if I want moment generating function of x plus a, some constant, right? We have the moment generating function of x with us. I want the moment generating function of x plus a, which is nothing but the expected value of e to the power of x plus a times t, which is nothing but e to the power of at times, right, expected value of e to the power of xt itself, which is mx of t. So if you have the moment generating function of of x, then you can very well find out the moment generating function of x plus a by multiplying the moment generating function of x with e to the power of at. So a constant is added, it gets converted into this mechanism. Whereas if you look at moment generating function of bx, you can very well write it as e to the power of expected value of e to the power of bx times t. So make it x times bt. So make it as moment generating a function of x with respect to bt, not with respect to t. Similarly, when there is a summation as well as a division, it becomes e to the power of a by b times t times moment generating function of x with respect to t by b instead of t. So these are some of the things which you can very well utilize if at all you want to solve a few additional numericals associated with the moment generating functions and the computation of moment, right? Now let's move on to the next topic within this, which is called as product movements. So when we are bringing in product movements, we are talking of pairwise now, right? Product movements are typically pairwise movements. So the r and s, product movements about the origin. So we are taking in two random variables x and y. So finding out the rth and the sth moment about the origin for the random variables x and y. So which is working out as expected value of x power r, y power s, which is also the same thing, x power r into y power s into f of xy, summed it over all values of x and all values of y in case of discrete, integrated over all values of x and all values of y in case of continuous. The same thing if I am trying to find out the product moments about the mean, we are doing the same, expected value of x minus mu to the power r multiplied by y minus mu y to the power s, which is as good as x minus mu x to the power of r into y minus mu y to the power of s multiplied by fxy summed over all values of x and all values of y in case of discrete, and integrated over all values of x and all values of y in case of continuous. Generally, the 1-1 relation, where I'm talking of r equal to 1, s equal to 1, which is nothing but expected value of x minus mu x times y minus mu y. This is a very important relation, which is otherwise called as covariance. So I really wanted to see the large values of x. The value, if this value of x is much above the mean, is the value of y also much above the mean? In this case, both of them will be positive. But if x is much lesser than the mean, y is also much lesser than the mean, then also the product is positive. So what this is typically signaling is this value would be positive if there is a high probability large values of x are going with large values of y, small values of x are going with small values of y. Right? So then the covariance will be positive. Covariance is how both of them are moving together. How when x is moving, if x is more and more high and positive, what is happening to y? Is it also high and positive? Or is it moving the other way? So that is one important thing that is coming out when we are using the word covariance. Large values of x are going with large values of y, small values of x are going with small values of y, or is it the reverse? If it is negative, we'll see the opposite moment. Large values of x go with small values of y, small values of x go with the large values of y. So we can very well see that that is called as covariance, and we know covariance is expected value of x minus mu x into y minus mu y. Expanded, it becomes expected value of xy minus x times mu y minus y times mu x plus mu x mu y. This becomes expected value of xy. Mu y times expected value of x is nothing but mu x. Mu x times expected value of y is mu y. Mu x y, mu x mu y. So these two are going up, making it expected value of xy, which is nothing but the first moment, 1-1 moment, minus mu x minus mu y. So expected value of xy minus expected value of x times expected value of y becomes the definition for covariance associated with a pair of variables. Let's look at a couple of numericals quickly to understand the relationships even more further. The joint and marginal probabilities of x and y, right, which are the number of aspirins and sedatives among the two caplets. This is the same example we are continuing. So for this, I want to find out the covariance, right? So x is 0, y is 0 is 1 by 6, x is 1, y is 0 is 1 by 3, x is 2, y is 0 is 1 by 12, and so on. Now I want to find out the covariance. So which is the expected value of xy. Okay, so x, y. Right, I can very well take x into y, 0 into 0 into 1 by 6. X, y, 1 by 6. Similarly, 0 into 1 into 1 by 3. Then it is 0 into 2 into 1 by 12. 1 into 0 into 2 by 9. 1 into 1 into 1 by 6. Then we have 2 into 0 into 1 by 36. I think all are zeros except only this one. So it is overall, the covariance is coming out to 1 by 6. So then no, this is expected value of xy. Sorry, expected value of xy is coming out to 1 by 6. Now we have already defined covariance is expected value of xy minus expected value of x into expected value of y. So I have to find expected value of x as well. So x is 0 into 5 by 12. I want to find the marginal distribution. So which is 0 into 5 by 12 plus 1 into 1 by 2 plus 2 into 1 by 12. So expected value of x is 1 by 2 plus 1 by 6, making it 4 by 6 or 2 by 3. So expected value of x is 2 by 3. Expected value of y is 0 into 7 by 12 plus 1 into 7 by 18 plus 2 into 1 by 36. So this is also 1 by 18. This is 7 by 18. 8 by 18 making it 4 by 9. So this is expected value of y. So covariance will become expected value of xy minus expected value of x into expected value of y. 1 by 6 minus 8 by 27. So making it 1 by 54. 9 2 into 8 16. Sorry, minus 7 by 54. Minus 7 by 54 is the covariance. So it's a negative, which is suggesting that if one variable is much higher, we are getting the other variable to be much lower. So that's how we can very well compute the covariance of in case of discrete variables through this kind of a mechanism. So we can also look at the continuous case, find the covariance of the random variables whose joint probability density is given by f of xy equal to 2, where x is greater than 0, y is greater than 0, x plus y is less than 1. So I want to find the covariance of this. Again, all else remaining the same. So let me take f of xy is equal to 2, right? So I should be able to find out each one of them. If I want to find out expected value of xy, I'll take, okay, I'm taking the value of x 0 to 1. X is greater than 0, y is also greater than 0, x plus y is less than 1. So x I am taking from 0 to 1, y I am taking it as from 0 to 1 minus x only, because x plus y is less than 1. X is, if I am taking from 0 to 1, y I am taking it as from 0 to 1 minus x itself. And f of xy is 2. F of xy times now expected value of xy means I have to multiply it with xy dx dy, right? Xy times f of xy, g of xy is xy, xy times f of xy dx dy. So I'm first I can very well simplify it with respect to y. So let me keep the x part. So y is y squared by 2, which is integrated between 1 minus x and 0, which works out as 0 to 1 2x. So I can y squared by 2, which is integrated between uh, 1 minus x so 2 I can very well take it out, which says x into, instead of y I am putting 1 minus x, so it becomes 1 minus x whole squared minus 0 squared is any of 0. So this is dx. So x into 1 minus x whole square. So 0 to 1, x into 1 minus 2x plus x squared dx, which is otherwise becoming x minus 2x squared plus x cubed dx. So x squared by 2, which is 1 by 2, minus 2 into x cubed by 3, 2 by 3, plus 3 into x power 4 by 4, which is 3 by 4. So overall working out to 1 by 2 plus 3 by 4 minus 2 by 3. Two x y squared by 2 x cube is x power 4 by 4, so this is only 1 by 4, making it 1 by 12. So expected value of xy comes out to be 1 by 12. Then I want to find out the expected value of x, which is mu x, wherein I am integrating from 0 to 1 and 0 to 1 minus x. I am taking only x times 2 dx dy. So it's only 2x. So if I am integrating it with respect to y, it is 2x into 1 minus x dx. So which is nothing but 2x minus 2x squared dx. So I'll get it as 2 into x squared by 2, which is 1 by 2, minus 2 into x cubed by 3, which is 1 by 3. So 1 minus 2 by 3 becoming 1 by 3. So this is expected value of x. Similarly, when you are finding expected value of y, the same thing, 0 to 1, 0 to 1 minus x, 2 into y dx dy. Integrate it with respect to y, it becomes 2 into y squared by 2. Y squared is nothing but 1 minus x whole squared by 2. This you are integrating it between 0 and 1. So 1 minus 2x plus x squared is what you are integrating between 0 and 1. So the integration of 1 is x, which is 1, minus 2 times x squared by 2 is 1 by 2, plus x cubed by 3 is 1 by 3. So these two are going off, becoming again 1 by 3. So expected value of y, mu y is also 1 by 3, mu x is also 1 by 3. So based on this, you can very well find out covariance, which is nothing but expected value of xy 1 by 12 minus expected value of x into expected value of y. So making it minus 1 by 36. So in this case also the covariance is very much negative. So covariance related numericals can quite comfortably be solved using this kind of mechanism. So if x and y are independent, we will see that the covariance will work out to be 0. So expected value of xy will be nothing but expected value of x into expected value of y. Then the covariance is going to work out to 0. But if two random variables are independent, I can very well say that their covariance will be 0. But the reverse, converse, if the covariance is 0, I cannot say that the two variables are independent. If the two variables are independent, I can very well say that their covariance will be 0. But if the covariance is 0, it is not necessary that the variables are independent. So we have to remember this statement very well, right? Independence means zero covariance, but zero covariance not necessarily means independence. So, and the other point is if x1, x2, xn are all independent, you will typically see that expected value of their product is same as individual expected values, the product of their individual expected values, just like expected value of xy is same as expected value of x into expected value of y. You could, if the joint probabilities, in case this is the case, right? For an example, you find whether this is independent or not, right? If the joint probability distribution is given like this, you could see that the covariance is 0 even though the two variables are not necessarily independent. So you could see here mu x, look at the expected value of x for this data, which is minus 1 into 1 by 3 plus 0 into 1 by 3 plus 1 into 1 by 3, which is making it completely 0. Mu x is 0. Expected value of y will be minus 1 into 2 by 3 plus 0 into 0 plus 1 into 1 by 3. So making it expected value of y is minus 1 by 3. Then what about expected value of xy? Minus 1 into minus 1, 1 into 1 by 6. So minus 1 into 0 I can forget. Minus 1 into 1, minus 1 into 1 by 6, minus 1 by 6. With zeros I can ignore everything. I'll take this 1 into minus 1, which is minus 1 into 1 by 6, minus 1 by 6. 1 into 1 plus 1 into 1 by 6, which is also 1 by 6. So expected value of xy is also coming out to be 0, right? So expected value of xy minus expected value of x into expected value of y, covariance is coming out to be 0. The two random variables, so the covariance is coming out to be 0. The two random variables are not necessarily independent, right? I cannot, if they have to be independent, I can even look at their, so here the covariance is coming out to be 0. You look at x is minus 1 and y equal to minus 1, the value is actually f of xy is 1 by 6. Whereas if you are looking at f of x times f of y, it is not equal to 1 by 6. 2 by 3 times 1 by 3, which is 2 by 9. So here the random variables are not necessarily independent. but the overall covariance has come out to be 0. So even those kind of things we should be able to understand. Then, moving on to the next important topic in this context, where I am taking the moments of linear combinations of random variables. So instead of taking a moment of x, I am talking about now the moment of a linear combination, let's say a1x or ax plus b. So we are talking about x1, xn as the random variables, right? Not just one. We are talking of different random variables x1, x2, xn, and we are talking about y as the linear combination ai xi. So a1 x1 plus a2 x2 plus a3 x3 so on. Then if I want expected value of y, which is nothing but I am taking a1 times expected value of x1 plus a2 times expected value of x2 so on. And similarly, so which is nothing but if I'm talking about a1 x1 plus a2 x2, right? This is much easier for you to understand. If I want the expected value of a1 x1 plus a2 x2, it becomes a1 into expected value of x1 plus a2 times expected value of x2. This is the expected value of linear combination of the random variable. Similarly, if you want variance of linear combination of random variables, this is one important concept that goes as a part of the portfolio theory. So this becomes a1 squared variance of x1, a2 squared variance of x2 plus 2a1 a2 covariance between x1 and x2. So this is the important formula, which is what is driving the overall concept of portfolio management itself. So which is nothing but it's different moments associated with the linear combination of the random variables. And if they are independent, because their covariances will be equal to 0, this term will not be existing, which will make variance of y as a1 squared variance of x1 plus variance a2 squared variance of x2 and so on. Now a quick example in this context. If I am looking at random variables x, y, z, they have a mean. Mu x is 2, mu y is minus 3, mu z equal to 4. Variance of x is 1, variance of y is 5, variance of z is 2. Covariance between x and y is minus 2, x and z is minus 1, yz is 1. Mean and variance of this. So mean of expected value of 3x minus y plus 2z. Expected value of 3x minus y plus 2z, which is nothing but 3 into expected value of x is 2 minus 1 into expected value of y is minus 3 plus 2 into expected value of z is 4. 6 plus 3, 9 plus 8, 17. This is the expected value. Now I want to find variance of 3x minus y plus 2z, which will become 9 into variance of x is 1, right, plus 1 into variance of y is 5, plus 4 into variance of z is 2, then 2xy, 2 into 3 into minus 1, minus 6 into covariance of xy minus 2 plus 2xz, 2 into 3, 6 into 2, 12 into covariance of xz is minus 1 plus 2yz, 2 into 2, 4 into minus 1, minus 4 into covariance of yz is 1. So this is what will give me the variance of 3x plus 2y, 3x minus y plus 2z. 9 plus 5, 14 plus 8, 22 plus 12, 34 minus 12. 22 minus 4, 18. 18 is coming out to be the variance of this particular linear combination. So that's a quick way to evaluate the moments of the linear combinations of the random variable. Right? If x1, x2, xn are random variables, y1 is ai, xi, a1, x1, a2, x2, so on. Y2 is again b1, x1 plus b2, x2 plus b3, x3, so on. Covariance between y1 and y2 will come out again the same way. I'll take the variances pairwise and I'll also take individual covariances. Probably this is much better explained through the example itself. So random variables x, y, z, they have the mean mu x. So mean is this much, x, y, z. Variances are this much. Covariances between x and y is 1, x and z is minus 3, y and z is 2. I want to find the covariance between u and v. So I can very well take covariance between x plus 4y plus 2z comma 3x minus y minus z. So which is nothing but for x's you take the variance. So 3 times x versus x. So you take it as variance. Variance of x is 8. Similarly, 4 into minus 1 becomes minus 4 times variance of y is 12. Similarly, z 2 into minus 1, which is minus 2 times variance of z is 18. Then take the pairwise, right? Where you are taking the pairwise x multiplied by y. So 1 into minus 1 and 4 into 3. X and y you are taking together. 1 into minus 1. Minus 1 plus 4 into 3 plus 12. So it is overall 11 times covariance of xy. Similarly, take x and z. 1 into minus 1, 2 into 3, 6. 6 minus 1, 5. 5 times covariance of xz, which is minus 3. Similarly, yz. 4 into minus 1 is minus 4. 2 into minus 1 is again minus 2. Minus 4 minus 2 is minus 6 times covariance between yz, which is 2. So overall it is working out to 24 minus 48, which is minus 24, minus 36, minus 60, minus 60 plus 11, minus 49, minus 15, minus 64, minus 12, minus 76 happens to be the covariance in this case. So I can very well find out the linear combination of the random variables, wherein I am looking at the mean, the variance, the standard deviation, and even covariances of a linear combination of random variables. So that's one more area where I think you should be comfortable with. Then, moving on to the next topic in this context, wherein I am looking at conditional expectation. So just like the way we had conditional probability, where we had x as a discrete random variable, f of x given y is nothing but the conditional probability distribution of x given y equal to y, and the conditional expectation of u of x given y equal to y. So you can very well say expected value of u of x given y equal to y. So which is, otherwise you take u of x multiplied with the conditional probability distribution of x given y and sum it over all the values of x in case of discrete, and integrate it over all values of x in case of continuous. So the mean of, if you are looking at conditional mean, which is nothing but expected value of x given y, whereas variance expected value of x minus the mean of x given y. So first you find the mean of x given y, and you find out the expected value of x minus of the mean of x given y, which is nothing but expected value of x squared given y minus the expected value of x given y whole square. So that's a typical formula kind of a mechanism. So you could very well take an example to really get a hold on it. F of xy is coming out to 2 by 3 times x plus 2y, for x lying between 0 and 1, y also lying between 0 and 1. I want to find out the conditional mean and conditional variance of x given y equal to 0.5, right? So I have to find out first of all f of x given y. F of x given y is nothing but f of xy by g of y, which is the marginal probability distribution of y. So I have to integrate it over all x to get g of y. So this is 0 to 1. I'm integrating it over all the x, and I'm taking only the y as 0 to y, integrating it over all values of x, the 2 by 3 x plus 2y. So which is nothing but 2 by 3 if I take it out, x plus 2y dx dy. Now I am trying to find out with respect to x. I am taking right, I can take the derivative with respect to x, making it x squared by 2, right, making it x squared by 2. So I'm integrating it over 1 to 0 to 1. So this is 1 by 2 plus 2y into x. So over 1. So this becomes 1 by 2 plus 2y. This integrated over 0 to y dy. So which will become 1 by 2 into y, which is y by 2, plus 2 into y squared by 2. Oh, I am integrating the marginal distribution. I don't require this one, so it is 2 by 3 times 0 to 1. If I'm integrating it, this is becoming 1 by 2, right? I'm integrating it with respect to x, so which is becoming 1 by 2 plus 2y, or 1 plus 4y by 2. So the f of xy is nothing but 2 by 3 times x plus 2y divided by g of y is 2 by 3 times 1 plus 4y by 2. So which is nothing but 2 into x plus 2y divided by 1 plus 4y, making it 2x plus 4y divided by 1 plus 4y. So this is becoming f of x given y, right? F of x given y equal to y is nothing but 2x plus 4y by 1 plus 4y. Now from here I am saying f of x given y equal to 0.5, which is nothing but 2x plus 4 into zero point 0.5 is 2, divided by 1 plus 4 into zero point 0.5 is 2. So by this is divided by 3. So f of x given y equal to zero point 0.5 is this much. Now I have to find out the expected value of x given y equal to zero point 0.5. So I have to take the integral of this 0 to 1 across the values of y. I am doing the integral of 2x by 2 by 3, 2x plus 2 by 3, 2 into x plus 2x plus 2 by 3 into x, x into 2x plus 2 by 3 dx. So which is nothing but, if I take each one out, 2 by 3 times x squared, the integral is x cubed by 3, which is 1 by 3, plus 2 by 3 times x. The integral of x is x squared by 2, so I can make it 1 by 2. So overall it is 2 by 9 plus 1 by 3, which works out to 5 by 9. This is the expected value of x given y equal to 0.5. Similarly, if I want to find out expected value of x squared given y equal to 0.5, instead of x here I have to set it as x squared. So this becomes 2 by 3 times x squared, the derivative, the x cube. X cube integral is x power 4 by 4 plus 2 by 3 times x squared, x cube by 3, 1 by 3. So making it 1 by 6 plus 2 by 9. So expected value of x squared is becoming 3 plus 4, 7 by 18. Expected value of x squared given y equal to 0.5 is 7 by 18. Expected value of x given y equal to 0.5 is 5 by 9. So based on that you can find out the variance, which is nothing but expected value of x squared given y equal to 0.5 minus expected value of x whole squared given y equal to 0.5. So making it 7 by 18 minus 25 by 81. So if I make it 162, 63 minus 50, making it 13 by 162 is the conditional variance that is associated with this random variable. So we will be able to find out the conditional expected value, conditional variance by doing the same kind of process. All we have to go ahead with is find out the conditional distribution function, right? And for the particular value of y, again find out the conditional distribution. Conditional is nothing but joint probability distribution divided by the marginal density function associated with that random variable, and based on that find out the conditional mean, conditional variance given a particular set of values. So that is what I wanted to offer as a part of this session. We have looked at expected value of the random variable, looked at the moments of a distribution of a random variable, focused on Chebyshev's theorems, worked on moment generating functions, how do you compute them, then looked at the product moments, focused on linear combinations of the random variables, and finally moved ahead towards the conditional expectation computation. Alright, if you have any further queries regarding the same, you can get back to me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@facegurus.com. Thanks a lot for listening to this session. Thank you very much.